You've heard that black holes swallow everything and never give anything back. But in this story, one of them might have done the opposite. It may have exploded, and Earth caught a single ghost particle from the blast. In 2023, deep under the Mediterranean, a detector called KM3NeT recorded the most energetic neutrino ever seen, a tiny particle carrying more focused energy than anything humans have made in a collider. No bright flash in the sky, no obvious source, just one silent hit that shouldn't exist if our current theories are complete. In this video, you're going to see how that one particle connects to primordial black holes from the first second of the universe, hidden dark forces, and the possibility that dark matter itself is made of ancient ticking time bombs that are only now starting to go off. But before we continue, please subscribe to the channel to give your support. Let's continue. You're in 2023, deep under the Mediterranean Sea. Above you, there are a couple of kilometers of water, around 2 to 3 kilometers, which is about 1.2 to 1.9 miles. Down here, the KM3NeT detector is running, a huge grid of light sensors sitting in cold, dark seawater. Most of the time, it just records ordinary background, tiny flashes that mean nothing special. Then, suddenly, an alert hits. The system flags an event that is way outside the usual range. A muon has passed through the detector with energy around 120 peta-electron volts. When the team does the reconstruction, they realize the muon could only have been created by a neutrino with around 220 peta-electron volts of energy. That number is so large it doesn't feel real at first sight. 220 quadrillion electron volts from a single particle that just hit near your underwater telescope. So what did you actually see down there? You saw a neutrino, one of the weakest interacting particles we know, hit something close to the KM3NeT lines and produce a muon that tore through the seawater. That muon moved fast enough through water that it emitted Cherenkov light, a cone of blue light, and dozens of optical modules lit up almost at once. On a screen, it shows up as a sharp, bright track, stretching over hundreds of meters, hundreds of yards, cutting sideways through the instrumented volume. For the people watching the data, it's instantly clear that this is not an everyday event. But big numbers on a screen don't mean much by themselves, so the next question you ask is simple and slightly uncomfortable. What does 220 peta-electron volts really mean in normal energy terms? If you convert that energy into joules, the standard SI unit for energy, you get about 0.035 joules. That is tiny. That's the kind of energy you use when you lightly toss a small pebble with your fingers. It's much less than the energy in a single step when you walk. If someone told you this event had 0.035 joules, you would not be impressed at all. The problem, and the reason this is so extreme, is where that energy sits. All of those 0.035 joules are concentrated into one neutrino. A single subatomic particle carried that whole amount. For comparison, the Large Hadron Collider near Geneva, a 27-kilometer ring about 17 miles around, accelerates protons up to around 1 trillion electron volts. That's already at the edge of what humanity can do with technology. This neutrino was roughly 100,000 times more energetic than those LHC protons. And when you compare it to the highest energy neutrinos previously detected, it's about 100 times more energetic than any of them. So you are looking at a particle that contains more focused energy than anything you have ever created in a lab. Yet nobody felt it, nobody heard anything, nobody saw a flash in the sky. It just quietly passed through Earth, and only because it finally hit something near KM3NeT did you even learn it existed. How can something that violent be so easy to miss? This is where the ghost particle label becomes important. Neutrinos are electrically neutral, they have no electric charge, and their mass is extremely small. They only feel the weak nuclear force and gravity. The weak force has a very short range, so interactions are rare, and gravity at the particle scale is incredibly tiny. That's why you can say, honestly, that trillions of neutrinos pass through your body every second, and almost none of them ever hit anything. When people call neutrinos ghosts, it's not poetry, it's just a description of how they behave. They go through walls, through rock, through water, through the entire Earth almost every time without leaving a trace. The only reason KM320-231A left a trace is that by chance, this one neutrino finally smacked into an atomic nucleus in or near the detector. It transferred its ridiculous energy to a muon, and that muon produced a clean, bright trail of light through the seawater that your sensors could see. So now you know the energy, and you know a ghost particle did this, but you still don't know where it came from. That's the next piece of the puzzle. The collaboration gives the event a name, KM320-231A. KM for the detector, 230213 for the date, 13th February 2023, and A because it's the first event like this tagged that day. They reconstruct the direction of the muon, and from that, they infer the direction of the original neutrino. The result is very specific and very strange. The track is almost horizontal, about 0.6 degrees above the horizon in the detector's local coordinates. In plain language, that means the neutrino came in almost sideways. It did not dive in from overhead. It entered Earth on the far side, traveled through thousands of kilometers of rock and metal, thousands of miles of dense matter, and then finally interacted near KM3NeT as it was exiting. A near-horizon trajectory like that is a strong signal that this is a neutrino from outer space that crossed almost the whole planet and not some particle created just above the detector by a local process. At this point, you can already say a few clear things. This was a neutrino. It had an energy around 220 peta-electron volts. It came from outside Earth, from a direction in the sky you can map. It passed through Earth and interacted near an underwater detector in the Mediterranean Sea. That alone makes it one of the strangest single particles humans have ever seen. The natural next question is, what kind of cosmic engine can do this? You start with the usual suspects. Active galactic nuclei, powered by supermassive black holes swallowing matter at the centers of galaxies. Gamma-ray bursts, triggered when massive stars collapse or when neutron stars merge and fire narrow jets of particles. These objects can push protons and heavier nuclei to extremely high energies, and when those primaries hit gas or radiation fields around them, they can produce neutrinos. In your models, these are the workhorse sources for high-energy neutrinos. But when you tune those models to try to get a 220 peta-electron volt neutrino, you hit problems. You have to assume unrealistically high efficiency in converting the energy of the jets into neutrinos. Or you have to align the jet with Earth in a very tight way. Or you have to push the physical conditions of the source to the edge of what seems reasonable. You can make it work on paper, but it feels forced. There's another issue. Real astrophysical sources don't only produce neutrinos at one energy. They produce a spectrum, a smooth distribution with many more particles at lower energies and fewer at higher energies. KM3230213A is so far out on the high energy end that it looks isolated. If this neutrino came from a standard source, you would expect to see many more events in the 10 to 50 peta-electron volt range coming from similar directions. Right now, this one looks lonely. And then you check for other signals. People search gamma-ray data, X-ray data, even gravitational wave alerts around the time and direction of the event. If something huge exploded or flared at that spot in the sky at that time, you might see it in another messenger. But nothing obvious shows up. No bright flare, no clear transient that lines up with the neutrino's origin. So here's the tension. Your standard picture of high-energy astrophysics says that known engines can make powerful neutrinos, but they struggle to make one this extreme without stretching the models. Observations in light and in gravitational waves don't clearly show a matching source, yet the neutrino is real, and the detector saw it. That's why you hear phrases like impossible neutrino. It doesn't literally break the rules of physics, but it doesn't fit comfortably into the toolkit you already have. It suggests that there might be a new kind of accelerator out there, maybe something involving dark matter, primordial black holes, or other physics you usually only talk about in theory papers. And that leads to the next question you have to face head on. What is this thing exactly, this neutrino that almost never interacts? And how do you turn ghost particles like this into a serious tool for understanding the universe? How can a neutrino that almost doesn't exist at all still be powerful enough to wreck your theories about how the universe works? Start with the neutrino itself, because if you don't get what this thing is, the rest of the story sounds exaggerated. A neutrino has no electric charge, so it doesn't feel electromagnetic forces. Its mass is so small that for a long time, physicists thought it might be exactly zero. Now we know it does have mass, but it's far below the mass of an electron, which is already tiny. It only talks to the universe through two channels, the weak nuclear force and gravity, and both of those are extremely quiet at the scales your everyday life cares about. If you could somehow shrink yourself down to the size of a proton and sit inside a block of matter, most neutrinos would still go straight past you, not stopping, not bouncing, not even slowing down. To them, you, your chair, and the entire planet are almost transparent. So here's the real question. If neutrinos barely interact, why do we care about them so much? Because weak doesn't mean unimportant. Weak just means rare interactions. A neutrino can carry huge energy, travel enormous distances, and still arrive at your detector basically unchanged. They're almost nothing, but when one of them finally does bump into something, especially at high energy, that almost nothing suddenly becomes a very loud piece of information. KM3NeT is the perfect example of that, a particle that ignored almost the whole universe until it finally tapped a single nucleus near KM3NeT and told you that some extreme process is going on out there. But if neutrinos interact so rarely, how many of them are actually around you right now? Is this a once-in-a-lifetime thing, or are you swimming in them all the time without knowing it? You are being hit by a neutrino fire hose constantly. Just from the sun alone, every second, something like hundreds of billions to about 1 trillion solar neutrinos stream through each square centimeter of your skin. That's each square centimeter, not your whole body. When you multiply that over your full surface area, you get hundreds of trillions of neutrinos passing through you every second. And that's just the sun. You also have neutrinos from cosmic rays filling the atmosphere, from old supernova explosions, from reactors, from all kinds of sources. Now scale up from you to the Earth. The Earth is about 12,742 kilometers across, roughly 7,921 miles. For high-energy neutrinos, that entire thickness is not a solid wall. It's more like a low-density fog. Most neutrinos just cross straight through and keep going into space on the other side. The chance of interaction is small, even over that much rock and metal. That's exactly why a neutrino like KM3NeT can enter on one side of the planet, exit near the Mediterranean, and only then finally interact near the detector. From the neutrino's point of view, Earth is almost a thin target. So if these particles are everywhere all the time, and almost none of them hit anything, how do you ever detect them in the first place, let alone study their direction and energy in detail? Detectors like KM3NeT and also IceCube in Antarctica use a very simple trick. They don't try to see the neutrino directly. They wait for the rare events where a neutrino actually hits an atomic nucleus in or near the detector, and then they watch the debris. In the case of a muon neutrino, that debris includes a muon, a heavier cousin of the electron. If the neutrino is very energetic, the muon comes out with a huge kick and moves through the detector medium at a speed that is faster than light can move in that same medium. Not faster than light in empty space, that's still forbidden, but faster than light's local speed in water or ice. When a charged particle does that, it emits Cherenkov radiation, a cone of blue light, kind of like an optical shock front. KM3NeT fills a cubic kilometer of seawater, about 0.24 cubic miles, with arrays of glass spheres, each containing sensitive light sensors. When a high-energy muon goes through, it triggers a pattern of flashes in these spheres. By looking at which modules lit up and exactly when they lit up, scientists can reconstruct where the muon went and how energetic it was. That's how they turned a few dozen glass spheres blinking in the dark into the statement, this neutrino had about 220 peta-electron volts, but energy is only half the story. Why does the direction of that muon track matter so much, especially for something that came from the other side of the planet? Here's the key point. Neutrinos are neutral. They don't feel magnetic fields the way charged particles do. Charged cosmic rays, like protons or nuclei, get bent and twisted by magnetic fields in galaxies, in galaxy clusters, and in intergalactic space. By the time they reach Earth, their paths are so scrambled that you can't just draw a straight line back to their source. You only see a blurred picture. A 220 peta-electron-volt neutrino is different. Over millions or even billions of light years, its path is basically a straight line with only tiny deviations. When that neutrino hits something near your detector and produces a muon, the muon carries almost the same direction. It's not perfect, but it's close. So if you reconstruct the muon's track accurately, you can point back to a tiny region of the sky, a small patch where that neutrino almost certainly came from. That's why KM3-230213A's almost horizontal track, just 0.6 degrees above the horizon, is such a big deal. It's not just a random line, it's a pointer. Now, put these ideas together and you get the real reason neutrinos are so important, especially at extreme energies. What makes them such dangerous objects for existing theories? Other messengers have limits. Charged cosmic rays get scrambled beyond recognition by magnetic fields. Photons, particles of light, can be absorbed or scattered by dust, gas, and background radiation. Gravitational waves are powerful, but they mostly tell you about massive collisions, like black hole mergers, not about all the messy particle physics around them. Neutrinos mostly ignore all of that. They don't care about magnetic fields, they usually don't get absorbed, and they don't scatter much. They carry a clean record of where they came from and how energetic the process was that created them. So when you see a neutrino at 220 peta-electron volts, you are forced to accept a hard conclusion. Something somewhere in the universe is accelerating particles to truly ridiculous energies, far beyond what you can reach on Earth. And because the neutrino got to you almost untouched, you can't blame the weirdness on the journey. The origin itself has to be extreme. That's why KM3-230213A's almost horizontal track, just 0.6 degrees above the horizon, is such a big deal. It's not just a random line, it's a pointer. So why would anyone turn a chunk of the deep Mediterranean Sea into a giant scientific instrument instead of just building another telescope on a mountain? KM3NeT exists because for ultra-high energy neutrinos, ordinary telescopes are useless. You can't focus ghost particles with mirrors or lenses. What you actually need is a huge, clear volume of matter where their rare collisions can light up in a way you can record. So KM3NeT takes about a cubic kilometer of seawater, roughly 1 cubic kilometer or 0.24 cubic miles, and fills it with vertical strings. Along each string, glass spheres are attached at regular intervals. Inside each sphere are photomultipliers, very sensitive light sensors that can detect tiny flashes. Put enough of these strings together and you get a three-dimensional grid of electronic eyes, all staring into the dark, waiting for Cherenkov light from passing particles. The seawater itself is the detection medium. When a high-energy muon from a neutrino interaction passes through that water, it emits that cone of blue light. The glass spheres don't care where the light came from, they just register when photons hit them. The key is that there are hundreds of these spheres, spread out over a volume the size of a city center. By comparing which spheres fired and when they fired, down to nanoseconds, you can reconstruct the path of the muon that caused it. One neutrino interaction becomes a pattern in space and time, and that pattern is what you analyze. So if KM3NeT is one detector, why do you keep hearing two different names, Arca and Orca, like there are two different beasts living under the sea? In reality, it's one project with two main configurations. Arca, which stands for Astroparticle Research with Cosmics in the Abyss, is deployed off the coast of Sicily, This part is tuned for ultra-high energy neutrinos, including monsters like KM3-230213A. Its lines are more widely spaced, optimized to catch long tracks and big bursts of Cherenkov light from very energetic particles. ORCA, oscillation research with cosmics in the abyss, is arranged differently and optimized for lower energy neutrinos, the kind you use to study neutrino masses and how they change flavor as they travel. Same basic idea, seawater plus photomultipliers, but different spacing, different energy focus, different science goals. This raises a simple question. Why bury both of these arrays 2 to 3 kilometers below the sea surface, around 1.2 to 1.9 miles, instead of closer to the top where it's easier to reach? That depth is your shield. At the surface, you're flooded with cosmic rays from space, constantly hitting the atmosphere and producing showers of secondary particles. Those would drown out the delicate signals you care about. By going a few kilometers down, you put a thick layer of water above the detector. That water absorbs most of the ordinary cosmic ray junk. What gets through are the truly rare, truly energetic particles that can punch through kilometers of rock and water, things like high-energy neutrinos coming from below. The Earth itself is part of the filter. Down here, when you see an upward-going track, you can be confident you're looking at something special, not just everyday noise from the atmosphere. If the detector is still under construction, how ready was it really when it caught KM3-230213A? Was this a fully finished machine, or more like a prototype? When KM3-230213A hit, only 21 detection lines were active. That is a partial build, not the full planned layout. Think of it as having only a subset of the cameras installed. Even so, that reduced array already covered a huge volume. The muon from KM3-230213A passed through that volume in such a clean, energetic way that those 21 lines were enough to capture a clear track and the precise timing pattern. As more lines are deployed, the angular resolution improves and the energy estimates become more robust. It's like adding more pixels to a sensor and more microphones to a sound array. The interesting part is that even this incomplete configuration was good enough to grab the most energetic neutrino ever seen, which tells you how powerful the full setup will be once it's finished. But how do you jump from "we saw some flashes" to "this muon had about 120 peta-electron volts and the neutrino that made it had about 220 peta-electron volts"? That sounds like a big leap. The muon from KM3-230213A left a trail hundreds of meters through the instrumented volume, hundreds of yards. Light sensors along that path recorded when they lit up, with timing precision better than a billionth of a second. From this, scientists reconstruct the muon's direction and the amount of light produced along its path. More energy in the muon means more Cherenkov photons overall, and a different distribution of light between nearby and distant modules. They compare the observed pattern to detailed simulations of muons with different energies crossing the detector from similar angles. The best match lands at about 120 peta-electron volts for the muon. The neutrino that made that muon started out with even more energy, because not all of it gets passed to the muon in the collision. Some goes into other particles, some into the target nucleus breaking apart. Based on interaction physics and statistical studies of many simulated events, you can estimate how much higher the neutrino energy likely was compared to the muon's energy. For KM3-230213A, that pushes the neutrino energy to around 220 peta-electron volts. There's uncertainty, of course, but not enough to rescue you from the basic conclusion. This was an extreme, record-breaking event. So now you have a detector that works. You understand how it turns seawater into a telescope, and you've verified that the energy estimate is not some software bug. The neutrino is real, the direction is real, the energy scale is real. The uncomfortable question you're left with is simple. If your instrument is doing its job correctly, and this particle really came from deep space at 220 peta-electron volts, why do your standard cosmic engines struggle so much to explain how it was made? If the universe already has some of the most violent machines you can think of, why does one single neutrino still push those machines to their limits? When you first see a 220 peta-electron volt neutrino, you don't immediately jump to new physics. You start with the usual suspects, the things you already know can accelerate particles to scary energies. At the top of that list are active galactic nuclei, AGN, powered by supermassive black holes in the centers of galaxies, and gamma-ray bursts, GRBs, from collapsing stars or merging neutron stars. Both of these are serious. They throw out jets moving at almost light speed. They shine across billions of light years, and they can already produce high-energy cosmic rays and neutrinos. So you plug KM320-213A into those models. You ask a very practical question. Can an AGN jet or a GRB jet boost a proton or a nucleus up to even higher energy than 220 peta-electron volts, then let it crash into gas or radiation near the source, and from that collision, create a neutrino with the energy you saw? On paper, in very aggressive scenarios, the answer can be yes, maybe. But to get there, you have to push everything to the edge. You need extremely strong magnetic fields, extremely fast shock waves, very compact acceleration regions, and almost no energy wasted. You're not in the comfort zone of those models anymore. You're at the far edge of what they allow. That leads straight into the next problem you run into, the energy budget versus what you actually observe. Think about an active galactic nucleus. The black hole may have a mass millions or billions of times that of the sun, and the accretion disk and jets can pump out more power than an entire galaxy. That sounds like more than enough to pay for one extreme neutrino. But when you do the math, you can't just say, it's big, so it's fine. You have to decide what fraction of that power goes into accelerated particles, what fraction of those particles are aimed in our direction, and what fraction of their energy ends up in neutrinos, especially in the very highest energies. To make KM320-213A in a standard AGN model, you often find yourself forced into two uncomfortably strong assumptions. One, the system has to convert energy into neutrinos with very high efficiency, much higher than you'd normally expect. Two, the jet has to be pointed almost exactly at Earth, so you're sitting in the bright, narrow core of the emission. That kind of perfect setup can happen for some blazars, AGN with jets aimed at us. But if you lean on that explanation too hard, you're basically fine-tuning the model just to save it. You're saying, it works if we happen to be in a very lucky and very special spot, which is not a satisfying answer. Even if you accept that, you still have to face the next question. Where is the rest of the neutrino spectrum that should come with this one? Real astrophysical sources don't spit out particles at only one energy. They give you a spectrum, usually something like a power law, where low-energy particles are common and high-energy ones are rare, but not isolated. If KM320-213A came from a normal population of AGN or GRBs, you'd expect a whole ladder of events below it, especially in the 10 to 50 peta-electron volt range. There should be a crowd of slightly less extreme neutrinos sitting under this one. Right now, this event looks lonely. It sits way out at the ultra-high energy end, with no obvious group of related events clustering just below it. You can argue that the statistics are still small and that more data might fill in that gap, but with what we see today, KM320-213A doesn't look like the top of a smooth curve. It looks like a spike that's hard to fit into the existing curve at all. That's another sign that maybe, just maybe, you're not dealing with a simple extension of known sources. Then there's the multi-messenger side of the story, which is where things get even more uncomfortable. If something out there is powerful enough to launch a 220 peta-electron volt neutrino at you, you'd expect it to shout in more than one way. After the detection, people went back and checked other observatories. Gamma-ray telescopes scanned their data around that time in that patch of sky. X-ray monitors did the same. Teams looked at gravitational wave alerts from detectors like LIGO and Virgo to see if a big merger lined up. The idea is simple. If a GRB went off there, or if an AGN had a flare, or if two compact objects collided, you might see a burst of high-energy light or a gravitational wave signal that you can match with the neutrino. What they found was basically nothing obvious. No bright gamma-ray burst screaming from that direction, no clear X-ray flare that says, a jet just went off here, no gravitational wave event with a matching time and position. Yes, it's always possible that a source was too faint for our telescopes, or too far away, or just happened to be in a part of the sky where our coverage is weak. But again, to keep the standard picture alive, you have to stack several maybes on top of each other. A source powerful enough to make a 220 peta-electron-volt neutrino is expected in many standard scenarios to leave some other trace, and here the sky is disturbingly quiet. So, you add up all these pieces. Known engines can, in principle, reach high energies, but they struggle to comfortably produce a neutrino this extreme, without fine-tuning. The energy budget looks strained unless you assume very high efficiency or perfect alignment. The expected spectrum below this event is thin or missing. Other messengers are mostly silent in that direction. That is why in talks and papers and articles, you see phrases like impossible neutrino attached to KM3NeT. Nobody is saying the laws of physics have failed. What they're saying is that this event does not sit easily inside any of the standard mechanisms you thought were enough. It's a stress test, and some of your models are creaking under the load. And when a single data point forces you into a corner like that, the natural reaction in high-energy astrophysics and cosmology is to widen the search. Maybe there's a whole class of cosmic accelerators you haven't really built into your picture yet. Things that don't look like normal AGN or normal GRBs. Maybe some of them don't shine much in light, or they hide in the dark sector, or they are tied to objects from the very early universe, like primordial black holes. So, if they formed that early, what could they look like today? Are we talking about tiny things, huge things, or both? The allowed range is wide. Models let primordial black holes have masses from around 100 billion kilograms, that's 10 to 11 kilograms, up to many orders of magnitude more, going through asteroid scales and beyond. 100 billion kilograms is big by human standards. It's more than a large mountain of rock, but in astrophysics, it's a small number. Then you have PBHs that could be as massive as big asteroids, or even heavier, yet compressed into tiny volumes. Here is the part that should bother your intuition. You can have an object with the mass of a mountain packed into something smaller than a marble, in extreme cases even down near the scale of an atom. If you tried to picture the mass of Mount Everest, roughly 10 to the 15 kilograms, packed into something smaller than a grain of sand, your normal sense of size and weight breaks. But that's exactly what a small PBH is: extreme mass in a tiny region, defined only by its gravitational field. It doesn't have a surface, it doesn't have a solid crust, it's just space-time curved so strongly that not even light can escape once it gets too close.
That sounds like it would just sit there forever, completely dark and boring. So where does Hawking radiation come into this story? In the 1970s, Stephen Hawking worked out what happens when you take quantum mechanics seriously near the event horizon of a black hole, the no-return boundary. Classical general relativity says a black hole is perfectly black, nothing comes out. But quantum field theory says there are always fluctuations, particle-antiparticle pairs popping in and out of existence near that boundary. When you combine these ideas, you find that black holes should slowly radiate particles, losing mass in the process. This radiation is called Hawking radiation. It behaves as if the black hole has a temperature. The heavier the black hole, the colder it is, and the slower it evaporates. A black hole with many times the sun's mass is colder than the cosmic microwave background, so it barely loses anything. It actually gains mass over time by absorbing background radiation. But a tiny black hole with much less mass has a higher temperature. It radiates faster, and over time, it can lose a lot of mass this way. As it loses mass, it gets even hotter, which makes it radiate even faster, so there's a feedback loop built in. That raises a critical question. If small PBHs radiate like that, shouldn't we have already seen them evaporate? And if we haven't, does that mean they don't exist? No one has directly seen a PBH yet, that part is true, but no direct detection is not the same as definitely not there. PBHs show up all over the place in theoretical work because they are a very natural tool. They are candidates for dark matter because they are massive, dark, and can be long-lived. They could help seed the first galaxies because even small black holes are great at pulling in gas. And they can explain certain weird gravitational lensing events, where a star briefly brightens as a very compact object passes in front of it and bends its light. Observations do put strong constraints on simple PBH models. For some mass ranges, especially ones where evaporations today would produce clear gamma-ray bursts, we don't see the expected signals, so those PBHs are either rare or missing. For other mass ranges, like certain asteroid mass windows, the limits are looser. More exotic versions where PBHs carry extra kinds of charge or interact with a dark sector can behave differently from the simplest case, and those are much harder to rule out. So why do cosmologists keep coming back to PBHs even though they're hard to pin down and might not even exist? Because if PBHs do exist, they give you information you can't get any other way. Their masses and how common they are directly linked to the density ripples in the early universe, right after inflation, when the universe expanded faster than light and stretched quantum fluctuations to cosmic scales. Those ripples eventually grew into galaxies and clusters, but PBHs would be the earliest possible collapsed objects formed out of them. Measure the PBH population and you're reading the imprint of those first ripples. It's like having fossils that date back to the first second of cosmic time. No normal star, no quasar, no galaxy can tell you that story as directly. That's why cosmologists secretly love PBHs, even if they're still hypothetical. They're not just weird black holes, they're probes of the initial conditions of the universe. And now connect this back to the impossible neutrino. If tiny ancient black holes really are out there, and if some of them are small enough to be strongly affected by Hawking radiation today, then their final stages of evaporation could dump huge amounts of energy into high-energy particles, including ultra-high-energy neutrinos. In other words, some of the most extreme particles you're seeing now could be the last signals from black holes that formed in the first instant after the Big Bang. The next step in the story is to ask a hard question. If small PBHs evaporate faster as they lose mass, does that end in a quiet fade-out or in a short, violent burst that looks a lot like an explosion? And could that kind of Hawking time bomb be exactly the kind of engine you need for a 220 peta-electron-volt neutrino? How can an object that traps light end its life by flooding the universe with radiation? In Hawking's picture, the key is a simple but brutal rule. The smaller the black hole, the hotter it is. Big black holes, the kind with many times the sun's mass, are incredibly cold. Their temperature is lower than the cosmic microwave background, the faint glow left over from the Big Bang. That background bathes everything at about 2.7 Kelvin, just a few degrees above absolute zero. A giant black hole is even colder than that, so instead of losing energy, it tends to absorb more radiation from its environment than it gives off. For all practical purposes, those monsters are not evaporating in any noticeable way. Tiny primordial black holes are a completely different story. If you take something far lighter than a mountain, compress it into a black hole, and calculate its Hawking temperature, you get enormous values. The smaller the mass, the higher the temperature. And at very low masses, the temperature is high enough that the black hole starts spitting out intense streams of high-energy particles. You're not talking about a gentle glow. You're talking about a hot object that can radiate photons, electrons, quarks, and importantly, neutrinos at energies that dwarf what your current accelerators can reach. So if small black holes radiate faster as they get lighter, what actually happens over their full lifetime? Do they just fade away or do they race toward a final outburst? As a primordial black hole radiates, it loses mass. Lose mass, temperature goes up. Temperature up, radiation rate goes up. Radiation rate up, mass drops even faster. You can hear the feedback loop in that chain. Early in its life, when the PBH is still relatively massive, the Hawking radiation trickled out slowly. The evaporation timescale is long, and nothing dramatic is happening. But as the mass shrinks, the process speeds up. Near the end, the system hits a runaway phase. The time it takes to lose each additional chunk of mass keeps getting shorter. The black hole gets hotter, radiates more, gets even hotter, and so on. Instead of a quiet fade out, you get a brief, intense burst, the time bomb phase people talk about. That naturally raises a practical question. If these things have been evaporating since the early universe, which ones are finishing now and which ones are still in the slow burn phase? Here, the mass really matters. The lifetime of a black hole due to Hawking radiation grows very fast with its mass. If you increase the mass a bit, the lifetime doesn't just go up a bit, it shoots up by a large factor. That means that only small PBHs below a certain mass would be reaching their final explosive stages today, roughly 13.8 billion years after the Big Bang. Very low mass PBHs would have already evaporated long ago. Heavier ones would still be around, evaporating so slowly that on human and even galactic scales, they look basically stable. So in the present universe, if PBHs exist at all, you expect three regimes. Very small ones that already died off, mid-mass ones that might be hitting their final phases now or in the near future, and heavier ones that are still just quietly bleeding energy at a rate that is almost impossible to notice. It's that middle group, the ones whose lifetimes line up with the age of the universe, that are interesting for ultra-high energy signals today. If that's true, shouldn't our telescopes already be seeing these final blasts all over the sky? And the fact that we don't means PBHs are rare, or maybe not there at all. Gamma-ray telescopes have been looking for exactly that. Instruments in space and on the ground have searched for short bursts of high-energy gamma rays that match what you'd expect from the last moments of a simple, neutral PBH evaporating. So far, there is no clear population of such bursts that you can say, with confidence, this is definitely PBH. That doesn't mean none exist. It just means you can set strong limits. If PBHs were common in certain mass ranges, their final flashes would show up in the gamma ray data more often than they do. Those limits cut down the simplest models, where PBHs have no charge and no extra interactions. But they don't kill every idea. More exotic versions, where PBHs can carry different kinds of charge or talk to a dark sector, can change how radiation comes out, how long they live, and how bright their final gamma ray flash is in our detectors. Some PBHs could also be too far away or too faint for current gamma ray instruments to see clearly, so the observational picture is tight but not completely closed. Now, connect this to ultra-high energy neutrinos. If you have a tiny, extremely hot black hole in its final moments, why is that such a good candidate for being a neutrino factory? In the late stages of evaporation, the temperature of the PBH is so high that it can emit almost any particle allowed by the laws of physics, not just photons. Quarks, gluons, electrons, positrons, and all kinds of heavier particles can be produced. Many of these then decay into secondary particles, spreading the energy over a whole zoo of species. Neutrinos are part of that zoo, and because they interact so weakly, they basically stream straight out without being reabsorbed. The energies involved can go into the peta-electron volt range, and even higher, up toward the exa-electron volt scale, especially in the very last instance when the temperature is at its peak. That makes a final Hawking burst a natural machine for producing the kind of extreme neutrinos you're dealing with in KM3NeT. It's not tuned for it, it's just a consequence of the temperature, the particle content, and the fact that neutrinos escape easily. So now you have a picture where tiny black holes formed in the first fraction of a second after the Big Bang spend billions of years slowly evaporating, then, for a very short time, blast out huge amounts of energy across all particle types, including a small but important subset of ultra-high energy neutrinos that can cross the universe and hit detectors like KM3NeT. But there's a catch you can't ignore.
Simple, neutral PBHs are already tightly constrained by gamma-ray searches. If you want them to be the engines behind events like KM3NeT you need a way to stretch their lifetimes, and a way to hide much of their visible emission, without killing the production of extreme neutrinos. That's where the idea of giving them a new kind of dark charge, a shadow version of electromagnetism, comes in as the next step. How do you make a black hole live longer, shine less in our telescopes, and still be able to launch insane energy neutrinos at you billions of years later? To do that, the model behind KM3NeT adds something new to the game, a dark version of electromagnetism. Right now, you're used to two main players around the black hole: gravity, which pulls everything in, and ordinary electric charge, which can make a black hole electrically charged if it swallows more of one charge than the other. In the new picture, there is a second, hidden force that only dark particles feel. It works in a similar way to electromagnetism, but it doesn't couple strongly to normal matter, and it doesn't light up your detectors. In that setup, a primordial black hole can carry not just normal electric charge, but also dark charge, linked to this hidden force. Technically, the geometry of the black hole changes when it has charge, even if that charge is dark. The closer you get to certain limits, where the charge and mass are finely balanced, the more the Hawking temperature gets suppressed. That's the key. You're using an invisible kind of charge to control how hot the black hole looks to Hawking radiation. If you have a dark force, you also get dark particles that carry and respond to it. The simplest examples are dark photons, which carry the dark force in the same way normal photons carry electromagnetism, and dark electrons, which carry dark charge in the same way normal electrons carry electric charge. They can have different masses and interaction strength than their visible cousins, but the basic idea is parallel. These dark photons and dark electrons barely talk to ordinary matter or light, if at all. That means your telescopes, which rely on ordinary photons, don't see them directly. But even if you can't see them, they still matter for the physics near a primordial black hole. When a primordial black hole radiates, it doesn't just emit normal particles. It can also emit dark sector particles if the right channels exist. The presence of dark charge and dark fields changes the way Hawking radiation is distributed, which types of particles are favored, and what the spectrum looks like. And this is where the quenching effect kicks in. If a PBH builds up a large dark charge, its effective temperature from the point of view of Hawking radiation can drop dramatically. You push it toward what's called an extremal or near-extremal state, where the charge and mass are close to a balance point. In that state, the black hole is still a black hole, but its Hawking temperature becomes very low. In plain language, it stops behaving like a hot, short-lived ember and starts behaving like a cold, long-lived rock. That has a direct effect on its lifetime. Instead of racing toward an explosive end, the evaporation almost stalls. The black hole continues to lose mass, but at a much slower rate. A neutral PBH of the same mass might have evaporated long before today, dumping its energy into the early universe. A dark-charged PBH with the same initial mass can hang around for billions of years longer because the Hawking fire has been turned way down. So what you've done, effectively, is to store energy for later. The PBH was born in the first fraction of a second after the Big Bang, but instead of finishing its life early and disappearing, it spent most of cosmic history in a low-temperature, dark-charged state. The fuse that Hawking radiation lit at the beginning was slowed almost to a crawl. Only now, in the present age, do some of these PBHs start drifting away from that perfectly balanced state, heating up again and heading toward a final burst. Thinking of it in simple terms, it's as if you lit a bomb at T=0, then somehow modify the chemistry so the fuse burns 1,000 trillion times slower, and only finishes right now, 13.8 billion years later. The original energy source is ancient, but the actual explosion happens today, in your observational window. That's exactly what you need if you want PBHs formed in the early fraction of a second after the Big Bang to still be producing extreme particles now. There's another important effect, which has to do with how visible these final bursts are in ordinary light. When a PBH evaporates without any dark sector complications, a big fraction of its energy comes out in particles that eventually produce gamma rays. That's what gamma ray telescopes have been looking for, final flashes from evaporating PBHs. The fact that we don't see a big population of those puts strong limits on the number of simple, neutral PBHs that can be out there. But once you include dark charge and dark particles, the mixture of emitted stuff changes. A significant fraction of the Hawking radiation can go into dark photons and dark electrons that we don't detect directly. That means the same energy budget can produce a much weaker gamma ray signal in our instruments because part of the energy quietly disappears into the dark sector. From our point of view, the explosion looks dimmer in gamma rays than it should be, even though the total energy and particle production are still large. This gives you a new way to hide explosions. You can have PBH bursts happening, but their electromagnetic signatures are muted, spread out, or mostly invisible to our telescopes. At the same time, neutrinos, especially ultra-high energy ones, still escape freely. They don't care whether the intermediate steps were dark photons, quarks, or something else. They only care that at some point, the small, hot black hole created particles that decayed into neutrinos at absurd energies, and those neutrinos had a clear path to space. So now the pieces line up. Dark charge slows evaporation, so PBHs are still around today. Dark radiation channels much of the gamma ray signal, so we're not flooded with obvious PBH bursts in our telescopes. Yet the final stages can still efficiently produce ultra-high energy neutrinos that can cross the universe and smack into detectors like KM3NeT. The next step is to look at a special case of these dark-charged PBHs, the so-called quasi-extremal ones, where the dark charge and mass are balanced so precisely that the black hole spends most of its life in a kind of frozen, long-lived middle age, and only very rarely tips into a violent final discharge. That specific behavior is what lets you connect one weird neutrino in 2023 to a whole hidden population of dark, fossil black holes making up the universe's missing mass. How can a black hole spend almost the whole age of the universe in a kind of frozen state, then in its last moments act like a grenade going off? Physicists use the word extremal for a very special kind of black hole, one where the charge and mass are tuned so precisely that the Hawking temperature drops to essentially zero. In that exact case, the black hole stops radiating, at least in the simple theory. Now, a primordial black hole with dark charge doesn't have to hit that perfect point. If it sits very close to it, with the dark charge and mass almost exactly balanced, they call it quasi-extremal. It's not truly zero temperature, but its Hawking radiation is heavily suppressed. From the outside, it looks like a black hole that should be hot and short-lived, but instead it's barely leaking anything. So what does a universe full of quasi-extremal PBHs actually look like over time? Are they noisy or are they basically dead quiet? In this quasi-extremal state, the PBH goes into a very long, very boring middle age. The temperature is low, the Hawking radiation is weak, and the mass loss is extremely slow. It still emits something, but the particles coming off are mostly low energy, and the total power is tiny compared to its mass. That means it can coast through billions of years, barely changing. On cosmic timescales, it behaves like a stable lump of dark matter, a compact object that contributes gravity but doesn't do anything dramatic. If you zoomed out and looked at a galaxy halo filled with these things, you'd just see extra mass, not fireworks. But if it's almost frozen like that, how do you ever get from this quiet state to an actual explosion? What breaks the balance? The answer is that nothing stays perfectly tuned forever. Tiny changes add up. Over time, even a quasi-extremal PBH slowly loses a bit of dark charge and a bit of mass. It might swallow the occasional normal or dark particle. Quantum effects might nudge its parameters. Each of those changes is small, but the balance it started with is very precise. As those small shifts accumulate, the PBH drifts away from the finely tuned quasi-extremal point. As soon as it starts to move away, its temperature responds. The suppression of Hawking radiation becomes less extreme, so the temperature creeps up. With higher temperature comes slightly stronger radiation. Stronger radiation makes the mass drop a bit faster. That makes the PBH move even further away from the quasi-extremal regime. It's a slow slide at first, but the direction is one way, away from frozen and toward active.
So what happens when that drift finally becomes big enough, when the black hole is no longer almost extremal, but clearly back in the normal hot regime? At that point, the PBH starts shedding dark charge faster. As it loses charge, its structure in the dark sector becomes less special. It transitions from this weird dark charged object towards a more ordinary neutral black hole. Neutral black holes at low mass don't stay cool. They heat up as they evaporate. So as the dark charge drops, the Hawking temperature climbs. The evaporation rate increases. It loses mass more quickly, which pushes the temperature higher still. This is where the runaway phase kicks in again. The PBH that spent billions of years barely changing now burns through a large fraction of its remaining mass in a relatively short time. Hawking radiation ramps up across all available channels. Normal photons, electrons, quarks, and neutrinos are produced, as well as dark photons and dark electrons that we can't see. From your point of view, this final stage looks like a short, violent evaporation phase, the explosion at the end of the PBH's life. It's in that phase that ultra-high energy neutrinos can be launched into space, with energies in the peta-electron volt to exa-electron volt range. Why does that help explain one strange neutrino in 2023 instead of flooding your detectors every day? The key is that only a small fraction of PBHs would reach this final discharge phase in any given slice of cosmic time. Most quasi-extremal PBHs are still locked in their long, boring middle age, radiating slowly, acting like dark matter. Only those that by chance have drifted far enough away from the balance point start to heat up and explode. That means the explosions are rare in space and time. You don't get a steady rain of Hawking bursts, you get scattered, isolated events. From the perspective of a detector like KM3NeT, that's translating to exactly what you're seeing now. You don't see 100, 200 peta-electron volt neutrinos. You see one standout event, KM3 with no obvious bright light source in the same direction and time. In the quasi-extremal PBH picture, that's not a bug, that's what you expect. A tiny fraction of the dark PBH population is reaching its end right now, and once in a while, one of those final outbursts sends a single extreme neutrino on a trajectory that happens to pass through 1 cubic kilometer of seawater under the Mediterranean and interact. So the scenario is this. An ancient black hole formed in the first instant after the Big Bang spends almost the entire age of the universe as a cold, dark lump. Then, because its near-perfect balance slowly drifts, it heats up, dumps its remaining energy in a brief violent phase, and one fragment of that energy reaches you as a 220 peta-electron volt ghost particle. The next question is, if that's what's really happening, where in the universe are these explosions actually taking place? And how does a burst from something smaller than an atom send a neutrino across hundreds of millions or billions of light years and still manage to hit a detector that, compared to the Earth, is almost unbelievably tiny? How far away can something be and still hit you with a single particle that breaks your record books? With a 220 peta-electron volt neutrino, the answer is very far. Because neutrinos interact so weakly, the universe is almost transparent to them, even over extreme distances. A particle at this energy can cross hundreds of millions, even billions of light years, and still have only a small chance of being absorbed or scattered. That means the exploding primordial black hole that launched KM3-230213A doesn't have to be anywhere near the Milky Way. It could be sitting in a galaxy on the other side of a cluster, in a small galaxy group a few tens of millions of light years away, or even in a faint satellite halo orbiting a larger galaxy. You are not limited to, this must have happened in our backyard. The source volume is huge. When you trace the reconstructed direction of the neutrino back into the sky, you're really drawing a very long, narrow line that can intersect countless possible host environments. Dwarf galaxies you barely see in optical surveys, dark matter halos with almost no stars, outer regions of bigger galaxies that look quiet in ordinary light. The weak interaction of the neutrino gives you a pointer, but not a precise distance, so the origin could be in a region of the universe that looks almost empty in normal telescopes. That leads to the obvious question. If a primordial black hole explodes, does it throw particles out evenly in all directions, or do you have to be in a special line of fire to see the really extreme stuff? In the simplest picture, the final evaporation is nearly spherical. The Hawking radiation comes out more or less in every direction. But once you look at the detailed particle physics, things get messier. The production and decay of heavy particles can introduce preferred directions. Local magnetic fields, nearby matter, and any rotation or residual structure in the PBH environment can make some directions slightly favored over others. The result is that even if the explosion starts off close to isotropic, some of the debris can end up mildly focused into broad outflows or jets, not razor-thin beams like in classic gamma-ray bursts, but not perfectly uniform either. In that case, Earth only sees the most extreme neutrinos from PBHs whose outflows line up roughly with our line of sight. For other explosions, you might only see lower energy neutrinos or none at all. That naturally makes the already rare ultra-high energy hits even rarer. So now think about the energy budget. How much total energy does one of these end-stage PBHs actually dump into space? And how much of that do you need to allocate to the single neutrino you caught? The total energy released when a primordial black hole finishes evaporating can be enormous, many orders of magnitude above the energy involved in a typical supernova. You're converting the entire remaining mass of the black hole into particles. Even a tiny black hole by astrophysical standards can carry a staggering amount of energy in its mass. But the part that matters for KM3-230213A is tiny. You only need a very small fraction of that total energy to go into the very highest energy neutrinos, in the 100 to 1000 peta-electron-volt range. The rest can be spread across lower energy neutrinos, photons, electrons, dark particles, and so on. From that huge spray of debris, KM3-230213A would just be one lucky neutrino that happened to be created in the right decay chain, at the right energy, aimed in the right direction, and then successfully traveled all the way to Earth without being absorbed. So this one particle isn't carrying the whole explosion on its back. It's just a sample, one data point out of an enormous particle shower you will almost certainly never see in full. On the way here, that neutrino passes through structure on every scale. It moves past galaxy clusters, regions packed with hundreds or thousands of galaxies. It flies through intergalactic gas, the thin plasma that fills the spaces between galaxies. It cuts across dark matter filaments, the invisible scaffolding that holds the cosmic web together. Photons would bounce, scatter, and sometimes get absorbed in these environments. Charged particles would spiral and twist in magnetic fields, losing all memory of their starting direction. The neutrino barely notices any of it. Over cosmic distances, it might have a few interactions, but the probability is low. And for a single trajectory, the most likely outcome is that it just keeps going, in nearly a straight line. That's why it preserves such a good pointer back to its source. The universe puts a lot of stuff in its way, and the neutrino just ignores almost all of it. By the time it reaches our solar system, you can think of the neutrino as essentially aiming at the entire Earth. But even then, the odds are still terrible. Earth's diameter is about 12,742 kilometers, roughly 7,918 miles. That sounds big, but the neutrino doesn't care about surfaces. It sees a line of possible interactions stretching through rock, metal, and water. Most of the time, even at 220 peta-electron volts, it would just pass straight through the planet and exit out the other side, never touching anything in a way you notice. Now, compare that with the size of KM3NeT. The effective instrumented volume is about 1 cubic kilometer of water, roughly 0.24 cubic miles, or around 260 billion liters, about 70 billion gallons. That's nothing compared to the full volume of Earth. It's a tiny, sparse grid of sensors in a very small region of the planet's outer shell. For KM3-230213A to become data, several things had to line up. The neutrino had to hit Earth at all, instead of missing the planet completely, which was already a small target on cosmic scales. It had to interact somewhere close enough to the KM3NeT lines that the muon track would pass through the array.
The interaction had to produce a muon moving in a direction and with an energy that made a clear, reconstructible light pattern. And all of that had to happen during the time that those 21 lines of the detector were active and recording. Given how small that instrumented volume is relative to the Earth, and how small the Earth is relative to the neutrino's potential path through the universe, the fact that KM3NeT saw this event is the real statistical shock. It's as if the universe fired an almost non-interacting bullet across unimaginable distances, and it just happened to hit a 1 cubic kilometer patch of seawater where humans had quietly placed a net of glass spheres. When something that improbable actually happens, you don't shrug and move on. You ask the next hard question. If even one such neutrino has been caught, and if the origin really is a small exploding black hole from the early universe, why haven't other detectors, like IceCube in Antarctica, reported matching events? And what does that mismatch tell you about how rare and directional these explosions really are? If this neutrino was so extreme, why didn't every big detector on Earth light up and scream about it at the same time? You've got KM3NeT under the Mediterranean, with roughly a cubic kilometer of seawater instrumented. You've also got IceCube at the South Pole, with about a cubic kilometer of Antarctic ice full of sensors. Both are built to catch high-energy neutrinos, so the first thing you ask is simple. Where was IceCube when KM3230213A hit? Here's the twist. IceCube did not report a matching event from the same direction and time. There was no clear, yes, we saw the same monster announcement. At first glance, that feels wrong. You'd think a 220 peta-electron-volt neutrino would be so extreme that any detector on the planet with a shot at that part of the sky would see something obvious. But the data so far says otherwise. KM3NeT saw it, IceCube didn't. So is that a contradiction, or are you just overestimating how similar these detectors really are? Different detectors see the sky in different ways. KM3NeT and IceCube are both cubic kilometer class, but they have different geometries, different optical properties in water versus ice, different trigger conditions, and different backgrounds. At a given time, each one has a different sweet spot on the sky, a region where upward-going neutrinos at certain energies are easier to pick out from the noise. KM3NeT is in the northern hemisphere, looking mainly at neutrinos that come up through Earth from the southern sky. IceCube, down at the South Pole, has its own set of preferred angles and energy ranges where the reconstruction is cleaner. For KM3230213A, the trajectory was almost horizontal, just about 0.6 degrees above the horizon in KM3's local frame. That's a very specific geometry. It's entirely plausible that this angle plus the energy plus the timing landed in a part of KM3NeT's parameter space that was very favorable, while putting IceCube in a less ideal configuration for seeing a clean, reconstructible counterpart. Maybe IceCube had a lot of atmospheric background in that direction at that moment. Maybe what it saw was buried in noise and didn't cross the threshold for a strong alert. So yes, in principle, two big detectors can see different things from the same event, just because of geometry and sensitivity. That already takes some of the mystery out, but it doesn't solve the deeper issue. Why do you have only one extreme event at all? If 220 peta-electron-volt neutrinos were common, both KM3NeT and IceCube should have catalogs full of them by now. These instruments have been running for years, watching the sky continuously. If known astrophysical sources like AGN and GRBs were routinely throwing out neutrinos at this energy, the statistics would reflect that. You'd see a handful here, a handful there, spread between detectors, not just a single outlier. The fact that you don't see that tells you something very direct. Either the sources capable of making such neutrinos are extremely rare, or their emission is so sporadic and so focused that your current dataset has just barely started to clip the edge of the distribution. In other words, this isn't a new everyday phenomenon. It's either a rare event or a rare alignment, or both. So which is it? Are you dealing with rare engines or rare geometry or some combination? In the dark charge PBH picture, you get both rarity in space and rarity in time automatically.
Only primordial black holes in a very specific quasi-extremal state with just the right dark charge and mass survive to the present while staying cold. Only a subset of those drift far enough away from that balance to heat up and explode now. And only some of those explosions will have their most extreme debris roughly lined up with Earth. That means you expect these events to be sparse. You don't fill the sky with continuous PBH fireworks. You get scattered, isolated bursts. Some might be completely invisible to your current instruments. Some might send only low-energy neutrinos towards you, blending into the background. And once in a while, one of them sends a very high-energy neutrino along a path that intersects a working detector and actually interacts inside it. One big detection in one detector, with nothing obvious elsewhere, is exactly the kind of pattern this model predicts, not a problem for it. But there's another angle here. What if the story is not one event and nothing else, but one very clear event sitting on top of a lot of partial, messy hints you haven't fully recognized yet? Some theorists have pointed out that both IceCube and other neutrino telescopes already have archives full of lower energy events in the tens of tera electron volt to a few peta electron volt range. Most of those get analyzed under standard astrophysical assumptions, as products of AGN, GRBs, star-forming galaxies, or cosmic ray interactions. But if PBH explosions are real, a fraction of those events could be the softer edges of the same phenomenon. Think about it this way. A single PBH explosion doesn't only make one 220 peta electron volt neutrino. It makes a whole spectrum with many more particles at lower energies. If Earth is not exactly on the most favorable line of sight, or if the detector only catches a small subset of the shower, you might only see that lower energy tail. Those detections would look like ordinary high-energy neutrinos, unless you specifically test them against a PBH model, checking their energy distribution, arrival directions, and possible clustering in time and space. So if that's true, then the pattern is already there, hiding in the noise. KM3-230213A is just the first unmistakable spike that forces you to reevaluate the rest of the data. It pushes you to ask, are there groups of events, maybe in both IceCube and KM3NeT, that line up with what you'd expect from occasional PBH explosions, even if each one by itself doesn't look dramatic? So the current situation looks like this. One very high-energy neutrino, clearly detected by KM3NeT with no bright electromagnetic counterpart and no matching IceCube event, but sitting on top of a background of other neutrinos that might already contain hints of the same engine. That's consistent with a picture where exploding, dark-charged primordial black holes are rare, directional, often hidden, and only occasionally send you one particle so extreme that you can't easily explain it away. And that leads to the next step. If these explosions are really happening, even rarely, then each one is not just a one-shot weird event. It's a one-shot physics experiment at energies way beyond what any human-built collider can reach. The natural question is, what kind of information about fundamental physics is encoded in the particle mix from a single PBH explosion? And how much can you extract from catching even just a few of the neutrinos that escape? What kind of event gives you almost every particle the universe allows at once and then never repeats the same way again? A primordial black hole explosion is basically a one-shot encyclopedia of physics. In its final moments, the temperature of the black hole is so high that it can produce almost any particle that is allowed by the underlying laws of nature. Not just the familiar ones from the standard model, like electrons, quarks, photons, and the known neutrinos, but also any extra particles that might exist in a larger theory, like dark photons, dark electrons, new heavy states, or things we haven't even named yet. In principle, the final burst contains a sample of everything that exists in the sense of being allowed by physics at that energy. The mix of particles that come out, the ratios between them, and the energies they carry together form a kind of complete inventory of what is really in the particle zoo. You are never going to build a machine on Earth that can survey the full high-energy content of the universe this way. A PBH explosion can, because it has gravity, quantum mechanics, and insane temperature all working together whether you like it or not. That raises a sharp comparison. If primordial black holes can do this, how far behind are your best human-made accelerators? Right now, the most powerful collider on Earth is the Large Hadron Collider. It reaches up into the tera-electron-volt range per collision. That's trillions of electron volts. That is already a huge technological achievement, using a 27-kilometer ring, about 17 miles, and enormous magnets and power. But a PBH in its final, hot phase is playing in the peta-electron-volt range and beyond, up toward the exa-electron-volt scale. That's millions to billions of times higher in energy than the LHC. So when you compare the two, you're not arguing over a small factor. You're comparing a very fast race car to the kind of speed you need to actually leave a planet's gravity for good. Both are moving, but one operates in a completely different regime. Colliders are great for precision work at lower energies. PBH explosions, if you can read them, are your only realistic way to probe how physics behaves at the very top end of the energy ladder. The important point is not just the maximum energy, but how the energy is distributed. The pattern of what comes out of the explosion is not random. The relative abundance of different particle types at different energies is controlled by the underlying theory. Change the theory and you change that pattern. If there are extra forces beyond the known ones, they will affect which particles are easy or hard to emit. If there are extra symmetries, they can protect some particles or enhance others. If there are extra dimensions or new kinds of fields, those can open new emission channels that wouldn't exist otherwise. So the full energy distribution of the particles in a PBH burst acts like a fingerprint. If you could somehow measure that distribution precisely, you could read off direct clues about new physics. You wouldn't be inferring things indirectly, you'd be looking at which particles actually came out, in what numbers, and at what energies. That would tell you whether dark charge is real, whether extra dark particles exist, and where simple models of black hole evaporation break down. But of course, you don't get to sit next to a PBH with a detector wrapped around it. Almost all of the information gets smashed, absorbed, or blurred before it ever reaches you. So which part of this particle catalog actually survives the trip across the universe in a clean way? Most of the particles from the explosion die locally. High-energy quarks and gluons hadronize, turning into jets of pions and other hadrons, which then decay. Photons scatter off surrounding matter and radiation fields, gradually losing energy or changing direction. Electrons and positrons spiral in magnetic fields and radiate away energy. Even some dark sector particles might get trapped or slowed down in their own hidden interactions. By the time you're looking at the rest of the universe, the original detailed pattern at the source is mostly scrambled. Neutrinos are the exception. They interact so weakly that once they're produced, they barely touch anything. They don't care about magnetic fields, they mostly ignore normal matter, and over cosmic distances, they lose almost no energy compared to other particles. A high-energy neutrino that leaves a PBH explosion is, to a very good approximation, the same neutrino that will arrive at your detector millions or billions of light years away. That's why measuring them is so valuable. Catching even a few neutrinos from a PBH explosion is like catching pure messages from the heart of the event, not just the messy leftovers after everything else has been processed and reprocessed. The energy of each neutrino and the number of neutrinos at different energies are direct probes of the original evaporation process. Now, look back at KM3NeT with that in mind. Even one ultra-high-energy neutrino already lets you start testing the ideas. That single event tells you that whatever the source was, it can reach at least 220 peta-electron volts in neutrino energy. That alone is a big constraint. It pushes you towards sources with extreme temperatures or extreme acceleration mechanisms. It pushes standard AGN and GRB models to their limits. It also gives support to models where small, hot black holes in their final phase naturally reach those energies without artificial tuning. In the dark-charged PBH picture, an event like KM3 20213A is a data point you can plug into detailed calculations. You can ask if PBHs carry dark charge, and if their evaporation is suppressed for most of their life, what does the final burst look like? And how often should it produce neutrinos in this energy band? You can compare the expected rate of such neutrinos with the fact that so far you've only caught one clear example. You can check whether gamma ray limits, neutrino data, and dark matter constraints can all be satisfied at once. With just one event, the error bars are huge. You can't prove the model, but you can start ruling out versions of the story that simply don't fit. You can say, for example, that models with no mechanism for ultra-high energy neutrinos are in trouble. You can say that any scenario where PBHs explode all the time is ruled out by the lack of a flood of similar events. Even that is already valuable. Now, imagine you don't just have one neutrino, but a handful, maybe a few tens over the next decade or two. Some at 200 peta-electron volts, some at 50, some at a few peta-electron volts, all coming from directions and times that make sense in a PBH story. Suddenly, the universe itself becomes a high-energy physics lab. You're not running a controlled accelerator experiment, but you are reading off natural events that happen at energies you can never engineer. Each neutrino adds another line to the data table, telling you how black holes evaporate, how the dark sector is structured, and what really lives at the highest energy scales. At that point, exploding primordial black holes stop being just a weird idea for exotic cosmology. They become tools. They turn the dark matter-dominated universe, the part you usually only see through gravity, into an active test bench for fundamental physics. Which raises the next critical question. If quasi-extremal primordial black holes can live for billions of years, explode rarely, and produce ultra-high energy neutrinos, could they also quietly make up most or even all of the dark matter that holds galaxies together? And if yes, how would every new explosion you detect help you map that hidden mass? How do you know most of the matter in the universe is invisible when you've never seen a single piece of it? You know dark matter is real because of gravity, not because of light. When you look at how galaxies spin, you see a problem right away. The stars in the outer parts of a galaxy move too fast to be held in by the gravity of the visible stars and gas alone. If only the stuff you can see was there, those outer stars should fly off into space. They don't. Something extra is pulling on them. You see the same problem in galaxy clusters. Galaxies inside the cluster move as if there's far more mass present than what you can add up from their stars, gas, and dust. On top of that, when background light passes by these clusters, it gets bent, a process called gravitational lensing. The amount of bending tells you how much mass is there. Again, the gravity says a lot, the visible matter says not enough. On even larger scales, when you simulate how structure in the universe grows from tiny early ripples into galaxies and clusters, you only get the observed pattern if you add a big component of unseen mass that doesn't interact with light. Add it up and you get a simple but harsh statement. About 85% of all matter in the universe is dark. It doesn't emit light, it doesn't absorb light, but it absolutely has gravity. So if there is this huge invisible mass, what is it actually made of? Really tiny particles or something else entirely? For decades, the default idea has been that dark matter is a new kind of particle gas. Very light particles, maybe heavier than protons, maybe lighter, drifting around in huge halos around galaxies. Weakly interacting massive particles, axions, sterile neutrinos, you've probably heard some of those names. What all of them have in common is that they're not black holes. They're individual particles filling space more or less smoothly. But primordial black holes have always been sitting there as another option. They have exactly the right basic qualities. They're heavy, so a relatively small number of them can add up to a lot of mass. They're dark because light can't escape them, and depending on their mass and their charge, they can be long-lived, surviving for billions of years, which is what you need to match the age of the universe. So people have been asking the same question for a long time. Could some of the dark matter actually be PBHs? Could they be, say, 10% or maybe 1% of the hidden mass? In many models, the answer is maybe in certain mass ranges, but not all of it because of various observational limits. Too many PBHs of the wrong mass would mess up lensing surveys or gamma-ray backgrounds or other signals. The dark-charged quasi-extremal PBH idea pushes this in a more radical direction. If you let primordial black holes carry dark charge and spend most of their lives in a quasi-extremal, almost frozen state, their evaporation is heavily suppressed. That lets them live much longer than simple neutral PBHs with the same mass. They look, for most of cosmic history, like stable, compact chunks of dark matter. In this picture, you don't need a gas of exotic particles to explain the missing mass. You can, in principle, fill dark halos with a vast population of tiny, nearly frozen PBHs instead. The claim in this model is bold. These quasi-extremal, dark-charged PBHs could account for essentially all of the observed dark matter. In plain language, almost all of the cosmic missing mass wouldn't be some invisible particle fog. It would be black holes, born in the first instant after the Big Bang, sitting everywhere in space right now, mostly quiet, occasionally dying. The dark matter halo of the Milky Way, in that view, is not a smooth particle cloud. It's an enormous, sparse swarm of ancient black holes. If that sounds extreme, the next question is obvious. How do you even start to test a claim like that? This is where explosions become a tool, not just a side effect. If dark-charged PBHs really make up most of the dark matter, then there are an enormous number of them spread through every galaxy, every cluster, and every dark halo. Most of them are stuck in that long, quasi-extremal middle age, radiating slowly, but a very small fraction should be reaching their end in any given era. Every time one of these dark PBHs tips out of its stable state and goes into its final discharge, it gives you information. The energy yield, the neutrino spectrum, how often you see such events, and where on the sky they appear, all feed back into the underlying PBH population. From each detected burst, especially those traced by ultra-high energy neutrinos, you can extract constraints on how many PBHs there are, what masses they tend to have, and how they're distributed in space. If you saw no such explosions at all over a long period, that would push against the idea that PBHs dominate dark matter. If you see a rate consistent with what the model expects, that supports it. KM3202313 is just one event, but it already nudges the balance, showing that at least one engine out there is capable of the kind of energy release you'd expect from a small dying PBH. So if dark matter is made of PBHs instead of a smooth particle gas, what does that do to your picture of how galaxies and stars first formed? Here, the story changes in a big way. If dark matter is a uniform particle fluid, then structure grows in a relatively smooth way. Tiny ripples grow into slightly denser regions, gas falls into those regions, and over time, you get the first stars and galaxies forming where the dark matter density is highest. There are no individual seeds, just small overdensities that grow. If dark matter is made of PBHs, you automatically have compact seeds built in. Some regions of the universe would have higher local PBH density. Gas falling into those regions sees not only a smooth gravitational background, but also specific points where gravity is extremely strong. PBHs can help pull gas together faster, possibly leading to earlier star formation in some places, or changing the typical masses of the first stars. They could also help form intermediate mass black holes early on, which then grow into the supermassive black holes you see in galaxy centers. That means a universe where dark matter is PBHs might have a different timeline for when the first galaxies appeared, how bright they were, how quickly supermassive black holes grew, and how the cosmic web developed. A single 220 peta-electron-volt neutrino doesn't rewrite that whole story by itself, but it starts to poke at it. It forces you to seriously consider whether some part of dark matter is not a simple particle soup, but a population of compact objects with their own life cycles and explosions. So you're left with a sharp choice. Either KM3202313 is an extreme fluke from known sources that just so happen to cooperate in all the right ways, or it's the first clear whisper from a dark matter population made of ancient black holes that are only now starting to die in detectable ways. And that leads to the next practical question you care about personally. If this model is right and quasi-extremal PBHs really make up the dark matter, how soon should you expect to see more of these explosions? And what are the chances that by the mid-2030s, your detectors will either confirm or crush this idea for good? If someone told you there's a roughly 9 out of 10 chance that humanity will see the first confirmed exploding black hole in the next decade, would you bet against that or start paying attention? In plain language, that's what the quasi-extremal primordial black hole model is claiming. When you fold in how many of these PBHs there would need to be to make up dark matter, how long they can sit in that long quasi-extremal middle age, and how often a small fraction should tip into their final explosive phase, you get a prediction. With the sensitivity of current and near-future neutrino detectors, the odds of catching at least one clear, unmistakable PBH explosion by around the year 2035 come out close to 90%. Not sometime in the distant future, not maybe in 1,000 years, but within the career span of the people currently working on these detectors, and very likely within your lifetime. So if the odds are that high, what exactly are we betting on changing between now and 2035? The answer is basically everything about how well we listen to the high-energy universe. KM3NeT under the Mediterranean is still being built out. Right now, you're talking about a partially complete array on its way to becoming a full cubic kilometer scale instrument, with dense lines of optical modules covering about 1 cubic kilometer of water, roughly 0.24 cubic miles. By the early 2030s, the plan is to have the full configuration running, giving much better coverage, angular resolution, and energy reconstruction than the 21-line snapshot that caught KM3230213A. At the South Pole, IceCube is planning its next phase, often called IceCube Gen 2. That expansion will add more strings and cover a significantly larger volume of ice, pushing the effective detection volume to several cubic kilometers, multiple cubic miles. On top of that, there's Baikal GVD in Lake Baikal, building another multi-cubic kilometer scale detector in freshwater, and large radio-based arrays coming online or expanding, designed to detect radio pulses from ultra-high energy particles interacting in ice, the atmosphere, or the lunar surface. Some of those radio instruments will effectively listen to volumes equivalent to many cubic kilometers, tens of cubic miles of ice or air. In other words, by 2035, you're not just repeating the KM3NeT and IceCube experiments with the same tools. You're surrounding the planet with bigger, more sensitive ears tuned to the exact energy range where PBH explosions are supposed to shout. But detection alone isn't enough. You need to decide what would actually count as a clear PBH explosion, not just another weird event that could still, with enough stretching, be blamed on a known source. For a real confirmation, one neutrino isn't ideal. What you'd like to see is a cluster of ultra-high energy neutrinos from the same region of the sky arriving over a relatively short window of time, maybe seconds to hours, depending on the details. Their energies should fall into the pattern predicted for a PBH evaporation, with a characteristic shape across the peta-electron volt range and beyond. On top of that, you might hope for a faint gamma ray or radio signal that lines up in both position and timing, even if it's much weaker than you'd expect from a normal gamma ray burst. Put simply, confirmation looks like this: multiple high-energy neutrinos, same patch of sky, same time frame, energy spread that makes sense for a tiny black hole blowing off its last mass, and no obvious standard astrophysical source that can account for it without heroic fine-tuning. That's the kind of event that would shift PBH evaporation from interesting speculation to observed phenomenon. Right now, you don't have that cluster. You have KM3230213A, one event.
So the honest question is, does that one event actually move the needle, or is it just noise dressed up in a fancy story? It does move the needle, because it proves something extremely basic but crucial. The universe is not empty at 220 peta-electron volts in neutrinos. Before this, you could reasonably hold the position that the neutrino spectrum might effectively cut off below that, either because known sources can't reach higher energies, or because the universe absorbs or suppresses such neutrinos before they reach you. Models that predicted events at these energies were easy to dismiss as nice math but probably irrelevant. KM3NeT kills that comfort. It shows, with real data, that at least once, somewhere, something accelerated particles or heated a system enough to spit out a neutrino at 220 peta-electron volts that survived all the way to Earth. That doesn't prove the PBH model is right, but it boosts the credibility of any theory that naturally makes such events, and it makes life harder for theories that assume this energy regime should be empty. One data point isn't a full curve, but it is a hard anchor. So now you have a model that says, if we're right, you'll see more of these by 2035, and a first event that says this energy range is actually populated. That sets up a very simple, very high-stakes countdown. Over the next decade, as KM3NeT finishes construction, as IceCube Gen 2 comes online, as Baikal GVD expands, and as radio arrays start probing ultra-high-energy neutrinos over enormous effective volumes, you'll be watching for patterns. If more extreme neutrinos show up, especially if a few form mini-clusters in time and direction that match PBH evaporation expectations, the PBH story gets stronger. The idea of dark-charged, quasi-extremal primordial black holes making up dark matter and occasionally exploding at the present epoch stops being a niche speculation and starts becoming a working part of your cosmology and particle physics picture. If, on the other hand, the sky stays quiet at these energies, the model gets squeezed. A lack of new events won't instantly kill it. You can always adjust parameters, tweak the PBH mass spectrum, tweak the dark charge distribution, but the more silence you see where the model expected noise, the more you're forced to admit that either PBHs are not the dominant dark matter component, or their explosions are rarer and weaker than advertised. Either way, something in your picture has to give. That's why this period, from now to roughly 2035, is not just waiting for data, it's a test window. The model makes a quantitative prediction about detection odds given detector growth. The universe will either cooperate and hand you more extreme neutrinos, or it won't. You don't get to negotiate with it. And that loops back to you personally. You're living in a decade where a single underwater detector has already recorded a neutrino your textbooks didn't really prepare you for, and where the next generation of instruments is being built specifically to catch more of them. Somewhere, either your standard models of particle physics and cosmology are about to be stretched to include dark charges and primordial black hole dark matter, or the PBH idea will be pushed into a corner, and you'll have to look for a different explanation for KM3NeT and any similar events that follow. Either way, by the time this informal 2035 deadline rolls around, something in your understanding of high-energy astrophysics, dark matter, or black holes will not survive unchanged. The countdown isn't just on the detectors project plans. It's baked into the physics of how long quasi-extremal PBHs can sit before they blow, and what you should see if they do. So the next natural question is, if one extreme neutrino and a decade of future detections can force that kind of rewrite, how many of your standard theories are actually standard, and how many are just low-energy approximations waiting to be broken by the first clear signal that the universe is running deeper, stranger rules underneath? How many of your standard theories would stay standard if exploding primordial black holes turn out to be real and powered by dark charges the current rulebook doesn't even mention? Start with the standard model of particle physics, the main theory you use to describe fundamental particles and forces. It has quarks, electrons, neutrinos, photons, gluons, W and Z bosons, and the Higgs. It has three forces built in: electromagnetism, the weak force, and the strong force, plus gravity sitting off to the side in general relativity. What it does not have is any of the stuff you've been talking about in this PBH scenario. No dark photons, no dark electrons, no dark charges, no dark version of electromagnetism. If dark charge and dark particles really exist, the standard model is incomplete in a very direct way. You don't just add one extra particle and call it a day. You add a whole extra interaction, a new gauge field that lets dark particles talk to each other. This new sector has to couple only very weakly to ordinary matter, or you would have seen its effects already in collider experiments and precision tests. That means you're extending the list of fields and forces with something that is mostly self-contained, a hidden network that only shares information with the visible sector through gravity and tiny portal couplings. That's a big shift. The standard model goes from the list of everything fundamental to the visible slice of a larger structure. The new PBH physics doesn't just tweak a constant, it asks for new building blocks. Now look at the other pillar, the cosmology playbook you use every A, the lambda cold dark matter model, LCDM. LCDM says the universe has a cosmological constant, that's the lambda part, which drives accelerated expansion, and a dark matter component made of cold, slow-moving particles, that's the CDM part. Those particles are assumed to be smooth on small scales early on, so the density fluctuations in the early universe are relatively simple. You evolve those fluctuations forward with gravity and expansion, and you get a large-scale structure pattern that matches what you see in galaxy surveys, at least to first order. Filling the dark sector with primordial black holes breaks some of those assumptions. PBHs are not a smooth particle fluid. They are compact objects, clumps. Even if they're spread out, they introduce granularity into the dark matter distribution. Early on, some regions would have more PBHs, some fewer. That changes how structure grows, especially on small and intermediate scales. You get extra seeds for collapse, extra points where gas can fall in, and possibly different timelines for when the first stars and galaxies ignite. LCDM can be adjusted to include some fraction of PBHs without collapsing. But if you say dark matter is basically all PBHs, you're doing more than a minor tweak. You're modifying the core assumption about what dark matter is. The simple picture of a cold particle gas has to be replaced with a population of compact remnants from the first second of the universe. That's not a cosmetic change. It's a new kind of dark matter model sitting on top of the same large-scale gravitational framework. And then there's Hawking radiation, which up to now has been a beautiful calculation with no direct observational proof. Hawking's result says black holes are not perfectly black. They slowly irradiate and evaporate, thanks to quantum effects near the event horizon. It's one of the most famous predictions in theoretical physics because it ties together general relativity, quantum mechanics, and thermodynamics. But it's also frustrating because for big black holes, the radiation is so weak you can't see it against the cosmic microwave background. A confirmed PBH explosion with the right energy spectrum would change that instantly. If you catch an event where the energies of the particles, the time profile, and the total output match what quantum evaporation predicts for a small black hole, you're not just supporting Hawking radiation, you're finally seeing it in action. That would be your first direct evidence that black holes really do evaporate quantum mechanically. It would be a new kind of laboratory, one where quantum field theory and curved spacetime, which has been mostly a theoretical playground, suddenly has real data to hit. Now, notice what's sitting in the middle of all this. An exploding PBH is the intersection point of three separate deep problems. You have general relativity, which describes the space-time geometry and the black hole itself. You have quantum mechanics and quantum field theory, which describe Hawking radiation, particle creation, and evaporation. And you have the dark sector with dark charge, dark photons, and dark electrons, which modify the black hole's temperature, lifetime, and emission channels. Normally, you study these areas in isolation. Gravity here, quantum fields there, dark matter somewhere else. In a dark charged PBH explosion, you don't get that luxury. All three are involved in the same phenomenon. The mass and charge structure is set by gravitational collapse and early universe cosmology. The evaporation is controlled by quantum field theory in a curved background. The detailed spectrum and lifetime depend on dark sector physics. When a 220 peta-electron volt neutrino from such an event hits your detector, you're probing all three domains at once. That's rare, and that's exactly why this kind of event is so valuable. So where does that leave your current standard models? Are they just wrong? If the PBH explanation for events like KM3NeT turns out to be right, it doesn't mean the standard model or LFDM are trash. It means they are effective theories, valid in the ranges where you first tested them. They work well at the energies of colliders, at the scales of galaxies and clusters, and in most of the data you've collected so far. But they are incomplete when you push beyond those ranges, into the ultra-high energy regime and the very early universe. In that case, we were wrong really means we were using a simplified version of a bigger theory. Dark electrons, dark photons, dark charges, and quasi-extremal PBHs would be part of that bigger theory. The existence of KM3NeT and any similar neutrinos becomes evidence that those deeper layers are real. The cracks where the bigger theory shows through are not failures, they're opportunities. They tell you exactly where to look if you want to move beyond today's textbooks.
So now the question shifts from, are our models right, to where exactly do they break first and how much can we learn from the first places they fail? Events like KM3-230213A are not just curiosities, they are stress tests. They hit the weak spots in your models and force them to either stretch, add new ingredients, or give way to something larger. And that brings the story back to you. You're not reading about this in a finished chapter of a physics textbook. You're watching it unfold while the data is still sparse, the arguments are still hot, and the next detection could tilt the balance. So the next thing to face is simple and personal. What does it actually mean for you to be living in the decade where the first exploding black hole might be confirmed? And how does that change the way you think about what's out there every time you look up? How often do you actually live in the moment where a physics story flips from settled to under attack right in front of you? Not over centuries, but over a couple of years of headlines and preprints. KM3-230213A hit in February 2023. The reconstruction, cross-checks, and analysis followed over the next months and years. Papers started to appear. People gave talks. Some pushed the primordial black hole idea. Others pushed back with more conservative models. You're not reading about this as a chapter that's already been cleaned up, simplified, and frozen into a textbook. You're watching the argument in real time, while the dataset is still small, while the main players are still trying to decide if this is a statistical fluke, a hint of new physics, or the first clear sign of a completely different dark sector. So what does that do to your picture of what's out there, the basic mental model you carry around when you think about the universe? You probably grew up with a simple line. Black holes are things that suck matter in and never let it out. They're the ultimate one-way objects. Maybe you heard about Hawking radiation as a theoretical twist, but it still sounds like a tiny, slow leak, not an explosion. Now you have to hold a second picture in your head at the same time. In that picture, some of the smallest black holes, born in the first instant after the Big Bang, are not just sitting quietly, they are on the edge of instability. Right now, somewhere out in a distant galaxy halo, there could be a black hole smaller than an atom in radius in its last moments of life, dumping its remaining mass into a storm of particles. Among them, a tiny fraction of ultra-high energy neutrinos break free and travel across hundreds of millions or billions of light years. One of those ghost particles might be on a collision course with Earth while you're listening to this. It doesn't care about your atmosphere, your satellites, your cities. It'll cross almost everything like it's not there, and only if it happens to hit a single nucleus in a cubic kilometer of water or ice do you ever find out it existed.
So here's the scale check you need to really feel how strange that is. KM3NeT is a structure a few kilometers across, a couple of miles, built out of vertical lines with glass spheres hanging on them, sitting 2 to 3 kilometers under the Mediterranean, about 1.2 to 1.9 miles. That's its whole world. It's not an orbiting observatory. It's not watching the entire sky in visible light. It's just watching that dark, cold volume of seawater for tiny blue flashes. The particle we've been talking about may have started its journey in a galaxy so far away that light from that galaxy has been traveling towards us for hundreds of millions or even billions of light years. That's distances measured in tens or hundreds of millions of light years, where one light year is about 9.46 trillion kilometers, about 7.58 trillion miles. So you're comparing a detector a few kilometers across to a flight path that could easily be 10 to the 22 or 10 to the 23 meters. If you want a crude human analogy, it's like putting a microphone in your backyard and picking up a single tiny crack somewhere on another continent. The numbers are worse than that, but the idea is the same. An absurd mismatch between the size of the detector and the distance the signal had to cross. KM3NeT, a thing only a few kilometers wide, is effectively listening to a volume that spans a huge chunk of the observable universe, and it only needs one successful interaction in 1 cubic kilometer of water, roughly 260 billion liters, about 70 billion gallons, to give you a discovery-level event. So the natural question is, what should you actually watch for next if you don't want to miss the moment when this moves from one weird event to this is real and we know it? In the next years, you should expect to see more announcements about ultra-high energy neutrino detections. Some will come from KM3NeT as more lines go live. Some will come from IceCube and its future Gen 2 upgrade. Some may come from Baikal GVD or from radio arrays that search for radio pulses from particle cascades in ice or the atmosphere. Most of those events will not be as extreme as KM3-230213A, but a few might creep into the same energy range. Pay attention to headlines and abstracts that combine certain words: primordial black holes, ultra-high energy neutrinos, Hawking evaporation, dark sector, dark charge, dark electrons. Watch for mentions of clusters of neutrinos from the same direction, or for events described as inconsistent with known source classes. Also, watch for joint analyses, where teams combine data from KM3NeT, IceCube, gamma-ray telescopes, and maybe radio arrays to argue for or against a PBH interpretation. Each of those is another piece in the puzzle, either tightening the case or pushing the theory into a corner. And here's the part that matters most for you going forward: how you react when you hear a line like "a single ghost particle carrying the energy of a thrown pebble hit Earth and may have come from an exploding black hole smaller than an atom." It's very easy to treat that as just another flashy space fact, one more wow line in a sea of cosmic trivia. But if you follow this whole story, you know it's not just trivia. That one sentence compresses almost everything we talked about. It encodes primordial black holes forming in the first fraction of a second after the Big Bang. It encodes Hawking radiation and the idea that black holes are not perfectly black. It encodes dark charge, dark photons, and dark electrons, hiding part of the explosion from your telescopes. It encodes the idea that dark matter itself might be a swarm of these things, sitting quietly in galaxy halos, occasionally dying in a way you can detect. And that encodes the simple, hard fact that your current standard models, the ones you learn in school, don't yet have tidy places to put all of that. The universe is not politely staying inside the lines you drew for it. It's handing you events that live outside the familiar energy ranges, outside the usual categories of sources, outside the particle lists printed on classroom posters. So when you think about KM3-230213A, don't just think breaking record neutrino. Think first crack, a place where the universe is quietly telling you the rulebook you've written is good for the easy stuff, for the low energy, nearby, well-lit regime. But underneath, at higher energies, in the dark, things run on rules that are stranger, deeper, and more radical than that. You happen to be alive right when the detectors are big enough, the data pipelines are fast enough, and the theories are flexible enough to start decoding those rules, not in an abstract future, but in your own decade, while you're scrolling past the headlines on your phone. And that means the next time a collaboration announces another impossible neutrino or the first convincing exploding black hole candidate, you'll know what that really is. Not just a cool story, but the universe showing its hand, one ghost particle at a time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.